To explain the Runge-Kutta method, let's rewrite back again the expansion for Taylor series for yi plus 1 using the point yi. But just to make the notation easier, let's say I replace yi plus 1 as y at t plus h. So t is our current time step, h is our step size. So t plus h would mean the value of y at the next step. So yi is replaced by yt. So if you use these two expression to rederive your Taylor series, this is what you have. Okay, so let's say the ODE that you want to solve is given by dy dt is equals to f at ty. Okay, so you know dy dt is your y prime. Okay, so instead of writing y prime here, let's say I substitute y prime with the right hand side of the ODE that you want to solve. So what happened then is we have y at t plus h is given by yt plus h, what is y prime, we're going to replace it with the right hand side. Okay, so here you have h squared 2 factorial. So y double prime effectively means the second order derivative. So since we do not have this expression, let's just leave y double prime as it is. Okay, so if you look at third order term, this is what you would have, and all the higher order terms. Okay, so we already know from the earlier part of this lecture that the accuracy of your numerical method to solve ODE can be improved if you include more terms from your Taylor series. So for example, if you want accuracy up to order h cube, you are going to include the term of from h squared as well. But let's say, to make things simple, let's say we want to find a solution of accuracy up to order h squared. So let's say this is the target that we want. If you want a solution up to accuracy h squared, what does it mean? It means that you have to find out what is y double prime. Okay, because you want to include this second order term right here. Okay, so in order to include this term, you need to know what is y double prime. Okay, so let me be clear it. So how do you find y double prime? We know that first of all, y double prime is given by the time derivative of y, simply your y prime. And what is y prime? From the ODE that we have that we want to solve, we know that y prime is just your right hand side function, which is f. So I can also write this as d by dt of f, t, and y. Okay, so now f here is a function of t and y, and you're taking a time derivative of your function f. So using chain rule, I will have y double prime to be written as partial derivative of f with respect to y, and you you add it with your partial derivative of f with respect to y, and the ordinary differential of dy dt. Okay, so this is from chain rule. So if you look at this equation, you have two partial derivatives and then you have a normal derivative, and normal derivative is dy dt. What is dy dt? dy dt is your ft. So instead of writing it as dy dt, let's say I rewrite this as f at ty. Okay, so now we have an expression of what y double prime is. This would still be roughly different from what we have earlier, because f here we know what function it is because it is always the right hand side of the ODE given to you. So what we want to do now is we want to replace this entire expression back into our y double prime. Okay, and if you do that, you are going to get y at t plus h is equals to yt plus hf at ty plus the second order term, and right now you're going to substitute your y double prime with that lengthy expression there. Okay, so I'm going to write the third order term y triple prime and so on. Okay, okay, I think here I've done a mistake. So instead of d by dy, this should have been partial derivative of f with respect to t. Okay, so once I substitute the expression for y double prime, I end up with this. Now, since we know what this function f is, because let me recap. Dy dt is equals to f as a function of t and y. So we would know what the expression for f is from the problem. So if we know what is f, theoretically we would know what is the partial derivative of f with respect to t and y. So if we know what are the partial derivatives, we would be able to solve this using Taylor series for order up to h to the power cube. Okay, so having to derive your df dt and df dy would go back to the same problem as your higher order Taylor series, because you cannot generalize it. So the Runge-Kutta theory basically says that the correct value of the slope over step can be written as a linear combination of the function f evaluated at certain points in the step. So what this basically means is that the value of the slope over a step, what is the slope? The slope, you know, is given by your function f. Okay, so it can be approximated as a linear combination of the function f evaluated at certain points in the step. So this is just the definition of the theory. To show you how the Runge-Kutta method is derived, let's go back to the Taylor series that we have. So the Taylor series that we have before, we can rearrange it to be written in this form. So this is the Taylor series that we have. What I've done is I'm going to rewrite this part here into this form. Okay, I'm going to rewrite into this form where you can see that I bring my h out, so I have h over 2 here and h over 2 here. Okay, now if you look at our expression here, you have your partial derivative of f with respect to t and y, and our objective right now is to write the partial derivative of f into some form that is simpler, that does not require further derivation depending on the problem. Okay, so what we notice from this expression is that the terms in this bracket here, it has the form that is similar to your two-dimensional Taylor series. So what is your two-dimensional Taylor series? Your two-dimensional Taylor series, if you don't recall, is given by this form over here. Okay, so given a generic function f at t plus alpha and y plus beta, so alpha is a small step increment in t, beta is a small step increment in y. Okay, so the Taylor series, or the two-dimensional Taylor series expansion for this function f at t plus alpha and y plus beta can be written as this format. So this is the general two-dimensional Taylor series form. Okay, so for simplicity, let's say these higher order terms that you see here. Okay, these are your higher order terms. Let's say we assume these higher order terms to be 0. Okay, so we're going to ignore all these higher order terms. So what we're interested in are this set of expressions here. So if you compare this expression and the terms in the brackets from your Taylor series, you can see some similarity there. So first of all, you have f as a function of t and y, so this would be similar to this, and you have df dt, which you have over here, and you have df dy, which you have right over here. So there's some form of similarity between the terms in the bracket and your two-dimensional Taylor series once you have ignored the higher order terms. Okay, so once you've seen this similarity, what you can say is that the value of alpha here would essentially be the same as h over 2 based on the similarity expression that we have. And if you look on this term over here, you can say that here you have your df dy and your df dy. So what you can say is beta is essentially given by h over 2 f as a function of t and y. Okay, so what this means is that our function f here can be written as t plus h over 2 y plus h over 2 f at ty. Okay, and this would be given by f at ty plus your h over 2 df dt plus h over 2 f times df dy. So all of this would be similar to all of this here, which means that you can substitute this expression back into the brackets. So if you substitute this left hand side expression back into this bracket, you will end up with this. Okay, now if you look at this particular expression, you will notice that this is actually similar to your midpoint method, because you can see if you recall from the previous lecture, what is the midpoint method? With the midpoint method, the first step is you are going to use Euler method to find out what is the value of y at the half time step. Okay, and then you are going to use the slope at the half time step to calculate the value at the next step. So this would be your yi plus h times f at I plus half. So your I plus half would have been evaluated at whatever you have over here. So that is the midpoint method, which is effectively captured by this, because if I compare, or let me rewrite it in full, so you have your f evaluated at t at I plus half and y at I plus half. Okay, so what is y at I plus half? Y at I plus half is given by yi plus h over 2 fi. Okay, if I rewrite this equation in terms of I and I plus 1, so y at t plus h would have been I plus 1. This would have been yi plus h times f t plus h over 2 would have been, sorry, let me rewrite it. It would have been f at t I plus half. Okay, and then you have your y, which is your yi, plus h over 2 f at I, meaning that you have f at I. So what you can say is that what you end up with this when you take higher order term is your midpoint method, and you can see that the midpoint method has a local error of order h cubed. So in the previous lecture, I've shown to you the error for Hume's method and Euler method without going through the derivation. And you can see from here how the order of accuracy of the Hume's and midpoint method are derived. They're essentially derived after we have considered higher order terms from our Taylor series. Okay, so what I want to show you here is that the Runge-Kutta method can be used to approximate the higher order derivatives. And by taking order of accuracy up to order h cubed, the Runge-Kutta method reduces to the midpoint method. So the midpoint method is essentially a second order Runge-Kutta method. So is the Hume's method. I won't show the derivation on how you can get the Hume's method from this Runge-Kutta approach. I believe the PowerPoint slides already have those derivations, so please go through them. Okay, so the key thing to remember from here is that by taking higher number of terms and using Runge-Kutta approximation, we are able to get a numerical method that is more accurate than the Euler method. And second order Runge-Kutta methods are essentially the Hume's method and the midpoint method.